Okay, this is my third try. All right, in 16.2, the question is, will a precipitate form? So we need to ask ourselves, is the solution saturated? Or, like, is there more stuff in solution than there's quote-unquote allowed to be? So basically what we're going to be comparing is Q and K and see which one's bigger. Okay. And remember, Q is calculated the same way as K, but the concentrations are not necessarily at equilibrium. They're just the present concentration. So you could have a Q that is less than K. And what does that mean? When Q is less than K, it means that the product of the ions concentrations is less than it would be if it was saturated. So basically we have less product than we would have if the system was at equilibrium. So we would say less product. So it'll be fully dissolved. There's not, like, we can't form any solid. It's not going to shift left. If anything, it would shift right, but there's no solid left. So it just doesn't go, it's not at equilibrium, effectively. Not every system can reach equilibrium, so this is one of those. However, Q is more than K. That's like you've stuffed more ions into solution than it can technically hold, so it's too much product. So we need to shift right, shift left, which will produce solid. So you'll have a solution that is saturated, and you'll have some solid. Undissolved solid. Present. Okay. Q is equal to K. This is this really improbable scenario in which, think about it for a second, there's just enough of each ion present to saturate it. No extra. There's no solid. This is really implausible. Okay. So let's ask ourselves, will a precipitate form? So we're going to calculate Q compared to K. In this case, we are dealing with two solutions mixing together and potentially forming a solid magnesium hydroxide. Okay, so we're going to imagine these two beakers. Okay, and they're going to be combining. Didn't do that right. Okay. This one has 100 mils, this one has 100 mils, the combined volume is 200 mils. Okay, this is 4.0 times 10 to the negative 4 molar, and it's magnesium nitrate. In this case, the question doesn't ask you anything about the nitrate or the sodium, so they are effectively irrelevant. So if you wanted to ignore them altogether, you could. There is a homework problem where they ask about those concentrations of the spectator ions, and then it's basically one of the first things we did at the beginning of the year was solution stoichiometry, where we did a race table and compared like the limiting reactant getting used up, and then how much of the excess is left over, and each ion floating around in solution, how much it had, and the new volume. And so you'll have to do that for 57 in the homework, and it's a little tricky, but you have the skills to do it. It's effectively like if at first we're just kind of ignoring equilibrium, and then we'll think about it as a second step. Okay, so here we have 100 mils, 100 mils, and 200 mils. Okay, so there's a couple ways you can think about this. Remember that for K expressions and Q expressions, we need to plug in concentrations. So if you wanted to, for concentration, you can always do, and this is what the solutions does, you can do moles over volume. And we would remember that moles would be MV from the initial solutions, right, this one or this one, divided by the new volume. So that's kind of a little, it's not a hairy calculation, but it's a little bit of a pain. The nice thing about this problem is because the solution volume is doubling, you can assume that the concentration of the ion in question will cut in half. So you can kind of cut past all of this stuff because it's sort of a waste of time. And if you're taking a 45-minute test, you're not drowning in time. So I would say to myself, okay, the magnesium nitrate concentration initially is 4 times 10 to the negative fourth, and then the concentrate or the solution volume doubles, the concentration of magnesium will cut in half. Okay, so 2 to 2.0 times 10 to the negative fourth. The important, okay, again, hydroxide, initially 2 times 10 to the negative fourth, concentration will half when the volume doubles, so its concentration will be 1.0 times 10 to the negative fourth. However, we have to remember that that is squared. So if you are going to make a mistake there with that, you need to first write your Q expression without anything plugged in, just so that you don't miss those exponents, okay? Okay, Q here is 2.0 times 10 to the negative 12. So we're going to deal with that in just a second. One more comment I wanted to make here is you do have to be careful in circumstances like if nitrate was the ion we were focusing on, we would have 2 things to bear in mind. One is the change in volume, but another is the subscript here. So if we were doing this question for nitrate, we would say, okay, the concentration of nitrate in this solution was 8 times 10 to the negative 4 because of the subscript. And then when the solution volume doubled, it went back down to 4 times 10 to the negative 4. So there's kind of 2 things that affect the concentration of an ion. The subscript in the original solution, in the original compound, as well as a change in volume. If the change in volume is hairier than this, it's going to be harder to do this in your head, so you might as well just do this. Okay, so back to this. When we compare Q and K, we find that Q is less than K, which means that this solution or this system does not have enough product for it to be at equilibrium, but because there isn't any more magnesium or hydroxide, there's nothing left to happen. It just will be an unsaturated solution. So the question is, will a precipitate form? The answer is no, it will not, because it is not able to saturate the solution. If you look at their work in the book, they did moles over volume, and they did a new volume, see, and they did, they actually used millimoles of all things. So again, same conclusion, more work, but do what works for you, okay? So lastly, I want to just briefly talk about what your questions are for the homework. It's 3 problems. Okay, we just did 53. 54 is like the twin problem, so that shouldn't be too hard. You do have some like differing, like here phosphase 1, here's 2, so I have to be careful, okay? You have to do 51, which is just what mass of zinc sulfide will dissolve in 300 mils of 0.05 molar zinc nitrate. So you already have zinc present, and you're trying to add in more solid to saturate it, okay? So that's kind of more common ion effect to me, but anyways, they're all kind of the same. Okay, 57 is kind of a doozy. So my advice for you, if you don't want advice, just pause the video. My advice for you, if you do want advice, is to think about it in 2 ways. The first way is if I gave you this problem in August, you would be able to do it, basically, almost completely. So you would say, okay, I have 2 solutions. I know basically the concentration and volume of each, which means I can find the moles of each if I care to. You now have the ability to do race tables, which you didn't have then, really. So you could kind of figure out what happens when they react and what's left, bearing in mind that the question gives you that you're forming this solid, which will not really have a concentration at the end, right? The difference is that you know that even if you form this insoluble solid, it does still dissolve a little tiny bit. So you'll have to bear in mind that after doing your rice table and thinking of this as a regular double replacement problem, you will have this equilibrium calculation to keep in mind, and to know that like one of these ions might be in excess, and the other one might have a quote-unquote concentration of 0 molar because it was a part of the limiting reaction, but we know that it wouldn't actually be 0 molar because everything dissolved to some extent, so you'd have to determine the actual concentration of that ion using the K expression. Okay, good luck with that one. We could definitely do another one like that in class on Thursday if it was